My name is Gary Newsted, and I'm a VMS addict. I was thinking on the long drive down from New Hampshire this morning that I'm getting old. I've been at this for a long time. I started with digital in 1981 at the ripe old age of 23. I'll do the math. I'm now 66. And VMS has been a part of my life that whole time. Through 4 companies, 4 architectures, at least a dozen CEOs, 3.5 marriages, and VMS is still VMS. All right, it's a part of me at this point. My daughter accuses me as I get older of breaking into random stories. You know, I guess that comes with age and experience. So I've decided, I'm going to approach this presentation as more of a story. The story of the Boot Manager, how it came to be, how it evolved, and how it continues to evolve today.
And you're a Clint Eastwood fan.
Yeah, he's a little older. All right, so the main agenda is shock and awe, and I'll talk about what that means. 24th of November, I got a phone call from Claire Grant saying, hey, we've got the rights to VMS and we're starting up a company. Are you in? At first I said no, but about 15 minutes later, I decided that's what I do best. So, okay, I'm in. So as of 24th of November, it'll be 10 years with the SI for me. Main part of the presentation today is the many faces of the Boot Manager. And I'll explain why I took on the Boot Manager and how it's become what it is today. And then, of course, this thing called virtual machines hit. And that really threw us for a loop. And I'll talk a little bit about what that implied for the Boot Manager. And then I'll talk briefly about this new thing called the guest console. Now, when I first agreed to work for VSI and I pulled in the parking lot down in Bolton, I noticed this big building with a lot of windows, but no cars. I'm thinking, where is everybody? I remember the other ports, we had a huge team of people. And to me, this was a shockingly small group of people to take on a task like porting to a new architecture. But at the same time, and over the next few days, I realized, but this was the right group of people to pull this off. Right? We had all the right people working on this. Sure, we'd like more, but it began to look like something we could do. Now, when I think of the evolution of the Boot Manager, I decided to put it in this context. The explorer, the builder, the loader, the driver, and the artist. There's a little bit of that throughout the design of the Boot Manager. When you first approach a wild architecture, one that you're not familiar with, your natural tendency is probably poke it with a stick. All right, let's poke at this thing. Let's see what's inside. Let's see if it bites. So I don't think anyone really had internalized what they would have been working on when we first started booting. People naturally gravitated to what they knew best. Drew was working on memory. A lot of people were still trying to locate the sources because the sources were mostly over in India and they didn't all come back. So we had a real mess on our hands to even get the sources. I thought the EFI environment would be a good place to start because EFI, the firmware interface, already ran on x86, right? So I figured, well, let's see what we can put together that would help us explore the x86 architecture. And some of the things we initially wanted to do, more as a diagnostic than anything else, see if we can read and write memory and various CSRs. A lot of these things turned into commands, which I have in red. Look at the memory map. see how it's laid out. Poke at ACPI, look at the UEFI services and see what we can pull out of EFI. Device probing was one of the first things we wanted to do. In addition to probing loadable devices, the CPU configuration is something we wanted to look at. And those of you that know x86 know that the CPU ID command is vast. There's a lot of information you can get about your processors. SM BIOS, well, not quite as useful, but there's a lot of information in there also. So the first thing the boot manager did is it provided us a means of looking at the machines, right? Looking at the hardware itself and poking around, which we did a lot of. This is just an example of what the memcheck command produces. And these are all color coded. I like colors. I use a lot of colors. VMS has memory descriptors that explain various types of memory. UEFI has another set of descriptors that explain what UEFI thinks that memory is for. So one of the first things we had to do is create some new memory types. I'll talk about memory disk in a little bit, but memory disk had to have its own memory type. The dump kernel had its own memory type. These are things that were new that we had to invent along the way. So this is just an example of dumping the memory range, looking at what EFI thinks it is. To EFI, it's either runtime data or loader code, loader data, things like that. So I have to map those memory types into something VMS would understand. At the end of this map, which can be huge if you have a lot of memory, I print out just a numeric list. This is just a linked list of all of the MCDs. And you can see in blue the special ones on the right-hand side. There's a new data structure for x86 called the kernel base. I'll talk a little bit about what that is. The hardware RPB is mapped in there, the memory disk. Down at the bottom, there's a shared one-to-one page table. This allows us to access UEFI runtime services physically. Even though the machine has gone virtual, we can still go through this one-to-one page table and access UEFI services. So there's some new things in there we had to figure out and invent along the way. This is an example of the dev check diagnostic. And what this does is it uses UEFI services to probe all of the buses on the machine. Let's just see what's out there. Let's look for controllers, look for multifunction adapters, bridges. Along the way, I try to identify if it's a bootable type disk. So there's a column there that says DK ? And where it's a bootable device, I enumerate the controller. One of the goals was to be able to use VMS device names from UEFI. I was told that couldn't be done, and they were right. but we managed to do it, and took a lot of iterations to get it right. And for the most part, it works. There's a few exceptions that I'll talk about. So the top section of this is just a probe of the entire PCI address space. And the real purpose for doing that is to set a bound for subsequent probes. So you're not sweeping the entire address space. You can very quickly look for controllers, but then in the second block up here, we're going back and really drilling down on each of those controllers to figure out what they are by class and subclass. And when we identify a bootable device in green here, we assign an actual controller letter to that controller. All right. And then at the bottom, we just sort of summarize. The comments in red over there are sort of important for virtual machines. The way that we identify that we're running as a virtual machine guest is that there are PCI vendor and device codes that say this is a virtual box, or this is KVM, or this is VMware. So right up front, I'm able to identify that we are in fact running as a guest. That becomes rather important later on. The dev CPU command does two things. First of all, this runs every time you load the boot manager. And it's looking to see if this processor has all the features we need to run VMS. And we have required features and we have some optional features that in this case, we passed the required features, but we're missing some of the optional instructions. That means that you can still boot, but it's probably going to run slow or have other issues. So we wanted to do that check right up front to make sure we're running on a compatible machine. If you continue, then I go ahead and break down all of the leaves of the CPU ID instruction. And I think there's about 20 pages of these things. So this is all the fine details of what that processor supports. In some cases, for instance, VirtualBox, we ran into a problem where it didn't have the Xsave instruction, which is an instruction we depend on. And yet, it's a brand new machine. It should have Xsave. And what was going on is that if you had, in this case, a laptop that had run Windows 11, they enabled Hyper-V by default. And so there's all these Hyper-V services that aren't allowing the guest to use the Xsave instruction. So we had to figure out a way to clear out Hyper-V from the machine, and all of a sudden, the guest now has the Xsave instruction. And there's a big, long release note about that. A lot of people even recently ran into that problem. The dev PCI command, again, probes the bounds of the PCI bus. And this time we're really drilling down, trying to figure out what each of these controllers are. And if they're a disk controller, we go ahead and identify the EFI device path. Here you can see HD 1, 2, and 3, 1, 2, and 3. Those are the three partitions of VMS. So now I know there's VMS on this machine. I see our three partitions. It's on a bootable disk. And that's why I can show you just the bootable devices. I don't show you everything, only the things that are bootable. The boot manager contains the entire registered PCI database, all vendors, all devices. All right. If you plug in a Walmart lava lamp, it would probably identify it. Well, it's compressed. It's not that big. A few K. So now keep in mind, we were running on real hardware at this point. So there was a lot more information in there than we need running on virtual machines. You have a pretty bounded set of devices on a virtual machine. And periodically, I have a utility that updates that database. If there's something that is not recognized, it'll print out curious device or curious vendor. That doesn't mean you can't use it if we have a driver. It just means it's curious, right? Something to look into. I should also point out that it has the entire USB vendor and database. Now that's changing rapidly. So that one you would really have to keep up to date. And we don't actually support USB right now. So that's not such a big issue. SM BIOS, there's probably 50 different SM BIOS tables that are registered. If they're registered tables, then I know how to break them down. And I show you the information that is in those tables. Now, unfortunately, there are also vendor-specific tables, and I have no way of breaking those down without the specs from the vendor. So in those cases, I just do a hex dump of what's in that table.
Could say curious.
Yeah. Curious thing, SM BIOS. All right, so we've now poked at the machine. We've mapped the memory. We've identified some new types. One other thing I wanted to mention about memory is you can also recycle a lot of the memory. And to give you an example of that, on a large HP server, like a ProLiant server, there could be upwards of a gigabyte of data that is used for UEFI boot services. Well, once you're done booting, you've just abandoned a gigabyte of data, right, or a gigabyte of memory. So what we do is mark those things that are recyclable. Some of the ACPI tables are recyclable. ACPI, by the way, is owned by UEFI. The two work together. So there's a lot of memory that can be recycled after you boot. It's a little bit tricky to do that. I'll talk about how we ended up using that in just a little bit. So the next thing we need to do as the boot manager is construct the structures that are required to boot the operating system. For instance, the hardware RPB. Is there anyone that doesn't know what that is? It's the restart parameter block. This is the main data structure that allows the boot manager to influence the operating system. It's the main interface between boot manager and the OS. I think I have a slide a little bit later that dumps the hardware RPB. A lot of information in there. I've also, at this point, refined that device list into just what we need to know for VMS. Is there a disk here? Is it a bootable disk? Is it a bootable VMS disk? What's its label? Things like that, so that I can print out a nice user-friendly display. The dev list command dumps that raw list. And more importantly, it recreates it every time you do a dev list command. So if we're having trouble with enumeration of devices, missing devices, things like that, we have a way to look behind the scenes at a little more detail. VMS device naming. Can it even be done? It took a lot of effort. VMS device naming is a really strange thing. The way we walk the ADP lists and identify the controller letters. For the most part, this is working flawless. Where you can trip it up is if you have a controller with no devices on it. Because, for instance, the boot manager has no idea about VMS. It really is a separate thing. I don't know that there are drivers for these devices. So if I see a controller, I'm going to enumerate it. Whether or not VMS supports it is a whole nother story. So if you have empty controllers, get them out of there. Otherwise, you'll end up with like a DKB where it should have been DKA device name. All right. So that's one known area that you can really confuse things. But that makes sense. Don't have orphan controllers out there. One of the other things I need to look at was the console interface. There's a lot more than meets the eye to a console. On one hand, it's very simple, right? It used to be just an RS-232 wire. Virtual machines changed that a little bit. The console needs to survive through a whole bunch of different mode changes. When you first start out, you're running purely physical, all right? As you boot, you need to stop partway into the boot for a conversational boot. So sysboot has to be able to use that console. When you continue from conversational, you go virtual. So now you're using that console interface virtually. Right. So to make that work as smoothly as possible, there's a new protocol that is used from the boot manager all the way until you're booted and you have runtime drivers. All right. That's known as just CON-IO protocol. So that was a decent amount of work right there. The kernel base structure that I mentioned earlier, actually, I'm going to come back to this one in just a moment. This is an example of the dev list command. And as you can see, it just breaks down each device. This is device 13 of 31. And it gives you the PCI information, UEFI information. Here we map it to the actual file system device, FS1. We give it a VMS device name. You can boot using either the VMS device name or the FS device name, whichever you prefer. Yeah, in Itanium, you always had to figure out what is the FS device. Here you don't, all right? But you can if you want. I also list the memory disk label as well as the EFI label and the VMS label where it's available. There's a little more information about partitioning down there at the bottom. I mentioned earlier the hardware RPB. There's a boot flag called the boot manager boot flag that just tells the boot manager, give me more information. And one of the things it does is it pauses every so often and says, do you want to see this structure or this structure? And it'll dump the structures. I've answered yes to dumping the hardware RPB, and this goes on for about 20 pages or so. But it's all the interpretation of the hardware RPB. There's a lot of stuff in there. All right, the next thing is my one animation here. So we've poked at the machine. We've built our critical data structures. The next thing is we want to load something. Maybe in early boot, it's a test program. Ideally, it's sysboot, because that's where we transfer to VMS. So the question is what to load, from where, to where, and how. All right. We don't have an operating system yet, so we don't have a way of loading drivers. We don't have drivers yet, so we don't have a way to load an operating system. So we've got a real conundrum here. So at this point, we got together with everyone that was part of ESI at that time, and we tossed around various ideas. In previous architectures, we had boot drivers or boo drivers, right? We didn't want to be in the business of writing boot drivers for every known device, right? That was just more trouble than it was worth. So can we find a better way? Well, we talked about network booting, all right? Because UEFI can get out on a network, maybe we can download something from a network and boot it. The problem is net booting is pretty complicated. In previous architectures, we're looking at roughly 140 files that make up the basic VMS kernel. Each of those files is individually downloaded, and the VMS loader had to create a in-memory disk image with all the expected directories, all the files in the correct directories. This was a nightmare. It was a huge part of the VMS loader that we just wanted to avoid. So again, is there a better way? At that point, we drove a stake in the ground and said there will be no boot drivers and there will be no primitive file system, because UEFI doesn't understand files 11 or ODS. These are foreign concepts, right? So we didn't want any of that. My significant other hates this little picture, but so we had the idea, well, why not put all those 140 files into a single container file and just download that one container file? Made a lot of sense. That became the memory disk, which is a dramatically new thing for VMS. Initially, it was just a simple command procedure that would look at a list, sys$memdisk.dat. This is on Itanium now. It would scoop up those files, put them in an LD container file, and we could load that one file, all right? We load that file using UEFI drivers, block drivers that are built into UEFI. UEFI already has drivers for every supported device, but they're just dumb block drivers. You just need a size and an LBN, and it'll put that file at that location. All right. So that's what we did. Now, the next question was, where are we going to store these files? At this point, we're building images on Itanium, but we want to get them over here to the x86 and load those images. Believe it or not, as I said here, USB was the obvious choice because at this point, most of us were working on laptops. We had a few machines in the lab, but we're still putting the lab together. All of these machines had USB, and UEFI has full support for USB. So what we did, I stopped one day at Best Buy on the way into work and bought a big bag of the cheapest USB sticks money can buy. I think they're like 70 cents each. And I littered these things all around. Anyone that had a need to load anything had these little colorful USB sticks, and they started popping up all over the lab. We created a port on the side of one of the machines that had this label, the fresh nectar port. All right. Some of you guys remember this. So whenever we did a build on Itanium, we would present that build to the fresh nectar port. You go down to the lab, plug in your USB stick, load it, take it to the machine you're testing on, and now UEFI and the boot manager could load that image. Right? So it was sort of an obvious way to do things that didn't violate our edict of no boot drivers and no file system knowledge. All right, so we've got a file. We've got a way of moving the file, SneakerNet. But we need to know how big this file is and where to load it. So the obvious answer is this LD container is a disk image, right? It's a logical disk. Why not use the boot block on the disk to say, here's the memory disk file and here's how big it is? All right. So at that point, we created what's known as the inner boot block. So the memory disk itself has its own boot block. It becomes a bootable entity by itself. And for the longest time, as more and more files are being ported and added to the memory disk, our command procedure would just create these boot blocks. And we would just load the entire thing in memory. The boot manager has no idea what it just loaded and doesn't care. But your image ended up in memory at the LBM that you chose. So we created the memory disk itself, which is still called sysdollarmd.dsk. It received a FAT32 partition called sysdollar.efi.sys because that's the only thing UEFI understands. It doesn't understand ODS, right? But it does understand a FAT32 partition. All right. In that partition, we put the boot manager itself and any other EFI diagnostics we needed. And then we had two more partitions in there known as OpenVMS sysdisk low and sysdisk high. And this is really just the three partitions that make up VMS. The files that fall below in LBN ranges, below where the memory disk is, or the EFI partition, excuse me, and then the files that are above that. Right? So VMS has these three partitions. We took the write boot utility and modified it to make an MD write boot utility. And this is what puts that inner boot block on the memory disk. All right, so the fields in the boot block contain the size and LBN and extent records of the memory disk and the offset within the memory disk where sysboot lives. This is the other thing that MD write boot does for us. We know here's where the memory disk is, and within there, here's where sysboot is. So we can now fish out sysboot based on information in the boot blocks. The ELF image header of sysboot itself tells us our transfer address, where we need to transfer control to jump into sysboot. All right, so all this stuff is packed into the image header or the inner boot blocks. This is just a lot more detail of how that whole thing works. But basically, it's a three-partition disk that has a master boot record, a weighted partition table with multiple entries for each of our three partitions. The only partition recognized by UEFI is that EFI partition. It contains the boot manager. But sysboot is out in the low ODS partition, right? So we have a pointer so that we can fish sysboot out of there and transfer control to it. I'm not going to spend much more time on that. Now we need to know where are we going to load it to. All right, we've got a way of creating these memory disk images. We've got the USB stick to move it. We've got the boot block to tell us what's on it. Now we need to know where to load it to. All right. So since we know the size of the memory disk image, the boot manager allocates a chunk of memory known as DMM0. You'll see this device on all x86 machines. Don't delete it. All right. That is the memory disk. That disk image remains throughout the whole runtime. All right, don't get rid of it. All right, critical files are in there, like everything you need to boot. So we allocate memory for DMM0. We load the memory disk in it. We fish sysboot out of there, copy it into its own memory, and then we get the transfer address out of sysboot's ELF image, do any relocations necessary, and we now have a transfer address. And at that point, we're off to the races. All right, we're able to successfully transfer control to VMS. And again, we didn't violate any of the edicts. No boot block or no boot drivers required. The boot manager has no knowledge of VMS file systems. This also means that the boot manager is fully decoupled from any specific version of VMS. You can run the boot manager entirely independent of the VMS version you're booting, right? Because it all works the same way. That creates some confusion, but it's also kind of nice. There's a command associated with this called mdcheck. mdcheck walks you right down the whole process of analyzing the inner boot blocks and setting up the transfer addresses. So that's kind of an interesting thing to poke around if you ever want to see how this works. This is just a quick example of the mdcheck diagnostic output. This is the GWDed partition table entry that has information for each of the three partitions. And you can kind of make out the three partition names on the right, x86, EFI, and then there's sysdisk low, sysdisk high. These are just telling it where on that memory disk these things are located. All right, so that was a lot of fun. All right, we now had a way to get this thing up and running. Well, Richard Bishop had a brainstorm at that point, and he said, let's do it again. All right. Well, why not allocate a second set of structures and load a second copy of the hardware B, RPV, and sysboot? All right, a la Galaxy, if you will. All right. That was the beginning of the dump kernel. When I said we weren't using boot drivers, well, boot drivers were used in previous architectures for booting and also crashing, right? So we needed some way to handle crash dumps, including a normal shutdown. So Richard got this idea, well, if we can create a second little kernel, DMM0 is already in memory, so it should boot really fast. We don't need to reload the memory disk. We just need to map sysboot into its own memory and map the hardware RPB into its own memory. So we now have two kernels, one that's going to be booted and one that's standing by, right, in a very small chunk of memory. So to make this work, when we fished sysboot out, it had relocation records in it, normal part of an ELF image. What we did was add an offset to those relocation records and load a second copy at the offset location, right? And if you dump the hardware RPV, you can see the kernel not kernel base. You'll see the base of both of the kernels, the normal kernel and the dump kernel. So now when we needed it to shut down or crash, VMS boots within seconds, right? The dump kernel has its own minimal startup file. So it's not interactive. You can't log into it. It just does the minimum amount necessary to take advantage of runtime drivers. And runtime drivers can dump memory a whole lot faster than the old boot drivers could, right? So it was a smart thing to do. The kernel base structure that I mentioned earlier is the one piece of data that's shared between both kernels. And the reason we share that is, one, so that the dump kernel can use console IO seamlessly. All right, so if you're crashing or shutting down, the primary kernel, which is using con IO, transfers control to sysboot. It picks up right where the primary kernel left off. It knows the row you were last on, the column you were last outputting to, and any other aspects of the console. So you get seamless transfer of console. Kernel base is also used by the dump kernel to store addresses of what needs to be dumped on the primary kernel. So Richard builds a whole map of what needs to be dumped. And when the dump kernel boots, it just looks at the kernel base structure, sweeps through those addresses, compresses and dumps the files. Very simple, right? This is just an example of the relocation records. If you set the boot manager flag, you see it loads a PSEC, copies it, load it, copy, loading, copy. So all it's doing is, as it's loading the first sysboot, it's making a copy of it into the separate memory required by the dump kernel. This, by the way, is why you should never, ever, ever set the boot manager flag and the verbose flag, because there were 5,158 relocation records, and it's more than happy to show you every single one of them. All right, so unless you've got about 2 hours to kill, don't use those two flags together. All right, finally, it's time to hit the road. We've got most of this working, but we don't have any disks yet. All right, so we had to take a look at what's required for runtime. We made a decision very early on to go with a SATA disk. And I think that was largely driven by the fact that, once again, our laptops and our machines in the lab both had SATA, right? So it made sense. We, until that point, didn't have a SATA driver. Rick Lord at the time modified our SCSI driver and created a SATA translation layer to translate the command set between the SCSI and a SATA disk. And then shortly after that, we added hard disk and DVD support to that driver. I'll talk a little bit more about DVD in a moment, DVD. So at this point, we're able to load full system disk images. All right, now keep in mind, all the engineers are porting as quickly as they can, as much as they can. The files in the memory disk are growing quite a bit. But we have a simple rule here. If it's required to boot, it belongs in the memory disk. If it's not required until you're up and running, it can be on the main disk. All right, we don't want that memory disk to just grow endlessly. Although an astute observer would maybe think of Internet of Things and what you could put in that memory disk without requiring a main disk, but that's another thing. We decided that if a device is a ISO image, in other words, a DVD, whether it's on hard disk or whether it's on optical media, we'll create a separate disk called DMM1. All right. The reason we create DMM1 only for ISOs is because it would take forever using UEFI block drives or block drivers if you were loading file by file. But if we load the entire thing, we can optimize those loads. I think it's like 32 KB per command. It enormously reduced the amount of time required to load the ISO image. So when you're doing an installation, the entire installation is copied into memory. And then from that point, it's a lot faster than if you were fishing files off the DVD. You don't have to keep spinning it up and things like that. So DMM1 only appears during installation. After installation, DMM1 goes away. Now keep in mind, DMM0 is our memory disk. So even if you load an installation to DMM1, you're still extracting DMM0 out of it and putting that in memory, and that has to stay. All right. But DMM1 goes away after an installation. About this time, we also experimented with NetBoot. NetBoot is based on an open source thing called iPXE or Internet PXE. iPXE is quite interesting. It allows you to network boot RAM disks, and you can go to iPXE.org and read about it yourself. We created a utility called VMS NetBoot that allowed us to just put our builds on our internal engineering web server, and you could netboot directly from that web server. There's a version of this that ships with all versions of VMS called KitBoot. The only difference between NetBoot and KitBoot is NetBoot knows about our engineering lab, right? Whereas KitBoot asks you for an IP address of your web server. So if you ever want to play around with this, there's also in the boot manager an install button or an install command. And if you use either of those command sources, it'll ask you for the IP address of your web server and the name of the image you're downloading. So you point it at an ISO image, it'll download and install it. We used this quite a bit initially, but once we had the whole disk mastering process up and running, the build process, this sort of fell out of favor. It's still there, but I don't think too many people are using it now. It'll come in handy again, though, as we get to like iSCSI booting, because iPXE already supports iSCSI booting and a lot of other advanced mechanisms. No, it's a whole different thing. Whole different thing. Where's Doug?
So is VSI going to have a different executive vice president in charge of?
Of iPXE? That's this little short dude.
You have the executive vice president in charge of the info server. Right?
Yeah. Yeah. Info server was the old 140 file method. Yeah. No, this is a lot simpler. This was also for our engineers that were not directly in the VSI lab, although it takes a long time if you're loading this to Europe over the internet. But it works. This is just another more detailed analysis of the back and forth that NetBoot performs. And again, the only difference is that we hard code the address in a pretty picture in a menu. You know, it's real nice. The customer version just asks you for the IP address of your web server and the name of the file. So at this point, the boot manager really needed to flesh out a bunch of different cases. I dubbed these things boot paths. Each one is unique. There's the local normal hard disk boot using 512 byte blocks, a local DVD ISO boot, which uses 2K blocks, local ISO on a hard disk, which uses 512 byte blocks, but with an ISO image. There's a network downloaded ISO downloaded to DMM1, a network system image. We can download an actual system disk rather than an ISO version. The memory disk itself is directly downloadable and bootable. And then we had one special case for HP's virtual CD, which uses a UEFI RAM disk. All right, so that was yet another special case. And with virtual machines, we're not interested in case 7 anymore. But the rest of these boot paths are, each one is unique. And if you set the boot manager flag, it'll walk you through which boot path it's using and anything unique about that. All right. The last thing is we wanted it to be pretty. All right. We, at least, I can't believe we're still looking at black and white terminals in this day and age. All right. And there's full graphic capability in UEFI. So I wanted to use it. What we ended up with is 4 distinct modes that the boot manager can operate in. The most simplest mode is serial mode, which is good old RS-232 with a wire. All right. Or if you're using a virtual machine with an emulated RS-232. Then there's rendered text mode, which is graphically rendered text without buttons and menus and things like that. Just raw text, but in color. Right? A lot of people like that. There's graphical mode, which has buttons. And then there's graphical I/O mode, which has mouse and touchpad support. Unfortunately, the virtual machines require a tools API to use the mouse. So that capability is there, but it only works on bare hardware. So what the boot manager does is it tries to use the highest possible graphical mode. If it can't, or it's disabled, it drops back mode by mode until it gets to the most primitive mode. Yeah. I don't support SPICE unless the virtual machine itself forces the use of it. As a UEFI app, I don't need to know SPICE. All right. If it's supported by the virtual machine, it can use SPICE. Oh, ask someone that knows. Yeah.
Host or how this actually supports it.
Yes.
So what do I need to get the boot manager console correctly in order to support SPICE?
I think you'll have to start by reading. I really haven't experimented with that. So sorry about that. The last thing I wanted to mention here is that there's a file out here that is called bmsimg.bmp. That is just a bitmap file. If you delete that file, you're going to end up in either mode 2 or 3. A lot of guys don't want a graphical display. All right, so just delete that bitmap and it will fall out of the graphical I/O mode into whatever mode it can support. If you do choose to use it, you can do pretty things. Like here, I've taken just a bitmap image and renamed it to that file name, and it scales it and puts it in the background of the boot manager. There's some restrictions. The box holding the buttons doesn't change, and this strip along the bottom doesn't change. But if you want your customer's logo or whatever, you know, you can just create your own bitmap image. Then we went virtual. Ooh, all this work. And then we decided, let's go virtual. Let's run on virtual machines. I almost died. I thought, oh my God, how is this going to work? Because now we're looking at VirtualBox, many flavors of KVM, VMware, ESXi Player, Fusion, Proxmox, Hyper-V, Zen, others. I was looking at those as being the equivalent of a new piece of hardware. All right, it's the wrong way to look at it, because a virtual machine, if it's doing its job, should look like a generic piece of hardware. All right. So I like to think that good design meant minimal change, because very little had to change with the boot manager to go to virtual machines. The truth is, I was just darn lucky. All right. All we need to do is add a few new PCI device names that allowed us to identify the type of virtual machine host. I added a field to the hardware RPB to tell VMS you're now running as a virtual box guest or as one of the other type hypervisors. Added a few new messages just to make it easy. Let the end user know that we know you're running as a virtual machine guest. Very little else had to change. So that was a real happy thing for me. This is just sort of what's on the near horizon. We're going to add some improved fiber channel support. Paul will be giving a talk on fiber channel Friday. Yeah. Improved network device support. I didn't talk much about network devices because, hey, they just seem to work. But I can tell you a lot more about network devices if I probe those devices a little bit further. And I've always wanted to do that. So we'll be adding iSCSI support. We have a group looking at the various tools APIs for the hypervisors that will allow us to do things like re-enable that darn mouse so we can now actually use the graphical I/O mode. There's a lot of features of the tools APIs, or a few features that are of interest to us. So we've got people looking at that. And the last thing, I'm going to ask my own question here. What's up with that suspended display? All right, anyone that's booted x86, you know that the boot manager suddenly goes blank and leaves a little message saying graphics output has been suspended.
Yeah, yeah.
Yeah, what's up with that? Well, here's the situation. UEFI, the firmware interface, created that window. It owns that window. I don't have any control over it. All right. When I'm done booting, the last thing I do is call a service called exit boot services. At that point, your protocols are dead. That window is abandoned, never to be used again, theoretically. All right. So the last thing I did was put out a message saying suspended. I didn't want just a black empty box on the screen. So we started talking about a problem that we ran into with VMware's vMotion, where you might want to move a virtual guest to another host. When you do that, you lose the console connection. It's a real pain in the neck. All right. So we started looking at, well, how can we solve this? This is something I've wanted to solve for decades. I wanted to get us off the RS-232 interface. And that's even more important now because when was the last time you saw a laptop with an RS-232 interface? Most machines have gotten rid of those per edict of Microsoft. The problem with an RS-232 interface is you can change whatever's plugged in there and the OS doesn't even know it. Right, so that's become a favorite spot for hackers to hack into machines. So they said no more RS-232. We're fortunate that the virtual machine hosts still support it, but you know it can be a real pain in the neck setting that up. All right, so it's a difficult interface. It has shortcomings. So I started looking at it, and I figured a display is a terrible thing to waste. That abandoned display is still mapped to the frame buffer memory. All right, the raw memory that's behind the graphics display. It's still mapped to that memory. You just have no protocol to talk to it. All right. So we created a protocol that can still take over that display. I can't resize it. All right. There's a limit to what I can do with it, but I can send text out there and I can handle keyboard input still. Once you've exited boot services, you're looking at a PS2 keyboard. Right? Might have been USB at one point, is now a PS2 keyboard. And you've got this raw bit of display, right? So we created a new driver for the guest console that knows how to take that display and continue using it, right? First, we prototyped a web-based console, and that worked pretty good, but we decided not to pursue it because of security issues, right? Just wasn't a very secure way to go. I looked at eliminating the console entirely, but that was a bridge too far, right? VMS depends on its console. So how about repurposing that suspended display? So what we did is create a new boot flag and a command called OPA 0. All right. So if you now type OPA 0, the GC driver will load, the guest console driver. When it loads, if it sees the serial driver loaded, the SR driver aborts, passes control to the GC driver, which grabs the OP driver, and you now have operator output to that guest console terminal. All right, so the serial and the guest console driver cooperate with each other, and one will get out of the way to let the other one have the operator terminal. And that's all controlled by the OPA 0 command, or no OPA if you want to turn it off. Embedded within the GC driver is the guest console terminal, which is a mostly full function terminal. ANSI compliant, has colors, can do limited graphics. The GC driver loads that terminal. Since we don't have mouse, I've had to implement page scrolling using the page up and page down button. Right? But the idea here is we have a terminal that doesn't require an RS-232 serial port. All right, so now vMotion works. All right, it can survive a vMotion transfer. There's no cut and paste because there's no way to select anything without a mouse. Right, so if we get our tools APIs working, now I can add cut and paste and mouse support, scrolling, things like that. Otherwise, this is a fairly fully functional terminal. Because I have no control over the size of the window, there's an important tip here. You need to set the page size to 2 lines bigger than the display. And that's because of the little status bar at the bottom of editors. Right, so it needs to be set slightly larger so that your paging works in the editor. But aside from that, this is meant for installation, limited use. I like it. I've been using it a lot, and this will continue to get better. The version that was shipped with field test was very limited. This next version has a lot more features, and I think that'll continue for a while longer. And that's just an example. It's a console. That's it.